Okay, hi everybody. If you're watching this, it means you want to take the gases test makeup. What I'd like you to do is take out your gases test, go through it as you watch this, figure out what you got wrong, and make sure you can get it right the second time so you'll get a much better score on your makeup. Here's the key. I'll go fairly fast, but you can pause this and rewatch anything you want, and hopefully your scores will improve. So let's go ahead and begin. The front page has the formulas you'll need. Let's go to the first problems. Problem number 1. You've got a system where the pressure is increasing, but the volume cannot change. So imagine, if you will, a can or something with fixed volume. What can make the pressure increase? Well, the temperature increasing can create a scary increase in pressure. This is known as Gay-Lussac's law. If the pressure cannot change, but the volume can, imagine a balloon, for example, that can get bigger or smaller. The volume will get smaller when the temperature gets smaller. This is known as Charles's law. Similarly, when you, let's repeat number 2. If the pressure is not changing, but the temperature is going down, this can happen. The volume is going down. Imagine a balloon, for example, where the volume can go down. This can happen when the temperature goes down. This is known as Charles's law. Similarly, when the temperature goes up, a balloon will get bigger, but the pressure will not change because it can expand rather than pressurize. So there you go, Charles's law. Temperature is proportional to volume. If you see more than 2 things changing at once, it has to be a combined effect, since all these other laws are 2 things changing and 1 thing being constant. This is the combined gas law. Note that if you take a good look at the ideal gas law, there's nothing really changing. It just explains a system where there's no change occurring. PV equals nRT. Okay, problem number 4. A sample of toxic hydrogen cyanide gas has a volume of 3.5 milliliters. So immediately write a letter for any units you see. That's volume. I changed it to liters in case it was the ideal gas law. That's the only one requires it. But I found out later it wasn't. I didn't change it back because I didn't feel like it. But you don't have to use liters if it's just a simple Charles's law, as this ends up being, because check it out. The temperature is 25 Celsius. Always change your temperature to Kelvin by adding 273 to Celsius, regardless of what law is at play. And then the temperature changes to 110. So I had to change that on the test to change, because I noticed that it actually decreases by a factor of 3 roughly, from about 300 to 100. We expect the volume to go down proportionally. So the answer should be, I don't know, 1-ish, 1.1 milliliters. And it turns out the answer is 1.29 milliliters, or 0.00129 liters. Either of those is fine. Since temperature and volume is at play, this is Charles's law. Problem number 5. What is the pressure? So write a big P equals question mark. On a 200 mil system, now let's see if we need to change to liters. We will if it's PV equals nRT. So I peek ahead and I see that we do have a pound of argon. I know that whenever you have a mass and a substance, you can figure out something known as N, the number of moles. Here's how I do it. If you have a pound, that's 453.6 grams. That's given. And I know from looking it up that argon has a molar mass of 40 grams per mole. I've got way more than 40 grams. In fact, I have 11.34 moles. Every time I have 40 grams, I have a mole. So divide by the molar mass to get the number of moles. It's a lot. And I notice that it's at 45 degrees C. Change it to Kelvin on the fly by adding 273. We should now have the units required for the ideal gas law. We have P's, we have V's, we have N's, we have T's. It must be PV equals nRT. This requires liters, atmosphere, mole, Kelvin. Rearrange if you like, and I do, to solve for P. There's your N, which we calculated right there. There's your R, it's always that number. Include your units. So few students do, but you'll see that everything cancels. Moles divided by moles. Everything will cancel except what you're looking for, which is atmospheres. You don't see any atmospheres in there. It's going to spit out atmospheres. Okay, so there's your 318 Kelvin for your T. That's the proper units. There's your P in liters. It requires liters. And so we have 1,480 atmospheres of pressure using the ideal gas law. Problem number 6. A mysterious gas needs to be identified. It's measured to have a density of 1.25 grams per liter. We always say for this class, where do you start? Start with what you're given. There's some units, there's some data there that's really the only data you're given. That's probably where you need to start, so write it down. And they want to know what it is. You can identify substances in various ways, but if you see STP, that means you're dealing probably with the Avogadro's principle, and that means that 22.4 liters is a mole, and we can get its molecular weight by multiplying grams per liter times liters per mole. Notice that liters cancels, and we get grams per mole. Start with what you're given, think about where you need to get to, which is grams per mole, and then either put the 22.4 liters on the top or the bottom, depending on what you need. And this substance has a molar mass of 27 grams per mole. Only HCN matches. Notice that ozone would be 48, 16 times 3. Water would be 18. But 1 plus 12 plus 14 equals 27 grams per mole. That gas is hydrogen cyanide. Problem number 7. Hang on. Okay, problem number 7. There we go. 10 grams of gaseous xenon tetrafluoride. Whenever I see grams and a substance, I know that I have moles. There's my hand. Okay, we have 10 207ths of a mole, right? Because if you add up these numbers, you get 207 grams as a mole. We only have 210 grams. To me, that always tells me set it up so it's way less than 1, and it is. Or if you want to memorize it, you put the molar mass on the bottom to convert to moles. Very low number, 0.0483 moles. That's your N. That tells you we have to use liters, atmosphere, mole, and Kelvin for solving the ideal gas law. The volume is given in liters, nice. The temperature is not, so we add 273 to our Celsius to get our temperature. Always write your letters nice and big so you convince yourself that the ideal gas law is at play here. Solving for pressure means P equals nRT over V when we rearrange. Just make sure you're using your liters, atmosphere, mole, Kelvin. There is our mole. There is our R, which has all 4 built in. There is our temperature in Kelvin, and there is our volume in liters. It should all be correct. We have 0.467 atmospheres, and off we go to problem number 8. A sample of oxygen has a volume, so write a big fat V, of 5 liters. At a pressure, write a big fat P of 200 millimeters of mercury. Read along to see if it's the ideal gas law. And I don't see anything that might be an N. I don't see moles or grams. So I'm going to keep it as just 200 millimeters of mercury, and I'm going to keep this as liters. Well, it's the right units anyhow. And it's going to increase its pressure, fine, and so that means the volume should go down. And hey, look, the volume's going down by half, 5 to 2.5. The pressure is going to double. The answer is going to be 400 millimeters of mercury, and it is. But go ahead and write down the formula, punch in your units with 1x. Don't just write numbers, write the units as well. Solve for x, 400 millimeters of mercury, bada bing. Problem number 9. A sample of hydrogen at 47 Celsius. I'm going to change that to Kelvin on the fly by adding 273. Exerts a pressure, so I'm going to write a P. I'm going to read ahead to see if it looks like ideal gas law. Once again, I don't see any identity of this substance. I don't see moles, so I'm just going to keep the pressure as millimeters of mercury. It's heated to 77. That's our T2. And I'm going to change that on the fly to 350, and I'm going to realize it's not going up by much, only 10% or so. So if the volume is constant, fine. That means I don't have to ignore it, and that convinces me that this is Gay-Lussac's law. He owns the TP. And there you go. What's the new pressure going to be? Write down the formula from your formula sheet. You don't have to memorize it. Solve for your new pressure and realize it should only go up about 10%, so I'm guessing 275 or something like that. And the answer is 273 millimeters of mercury. If you get here and don't know how to solve it, realize you can cross multiply. X times this equals that times that. And if you do it often enough, you realize it always equals X equals this times this divided by that. And I do that, and that's my answer. Make sure your units cancel. Kelvin divided by Kelvin cancels. I hope the answer is millimeters of mercury. Pressure, yeah, looks good. Last problem, probably the hardest one. We rehearsed this many times in class. How many liters of pure oxygen, so they want volume, measured at 740 millimeters. We're not at standard temperature and pressure. It sounds like ideal gas law, right? A V, a P, which, so I'm going to go ahead and change it to atmospheres. And I'm burning 1,000 grams of tetrahydrofuran. Well, I could get N for tetrahydrofuran, but I'm solving for the liters of oxygen, so I better make sure I know what I'm doing here. Why don't I figure out how many moles of oxygen are needed and then convert to volume using PV equals nRT? Well, they don't give us how much oxygen is involved, but I can figure that out because I'm burning 1,000 grams of THF. I start with a balanced chemical equation. 8 carbons, 8 carbons. As written, 16 oxygens, 16 oxygens. And you'll see that it's 2, 11, 2, 8 to 8. Fine, I hope you know how to do those balanced chemical equations. Hint, save oxygen for last. Total those up and make that number equal it. Even if you have to use half a number, double everything if you do. I hope that helps. And then do our two-step grams of THF. That's what I'm going to call tetrahydrofuran. 2 moles of oxygen. In this class, we can use a template to help us along. And anytime you have 72 grams of C4H8O, that means 48 plus 8 is 56 plus 16 is 72. That's a mole of THF. Grams of THF cancels. Anytime I have 2 moles, and I got that from here, 2, of THF, it's already canceled. It requires 11 moles of oxygen. Wow, that's a lot of oxygen. Punch that in and you get 76.4 moles of oxygen. That's your N for oxygen, which we need. We can now calculate liters of oxygen because we have enough data given to solve for PV equals nRT, which I already rearranged there. There's your N in moles, R, 0.0821 always, temperature in Kelvin, pressure in atmospheres. 760 millimeters of mercury is an atmosphere, and we have almost that much. If you divide by 760, you can convert from millimeters of mercury to atmospheres. Punch it all in, and we find out that this requires 1,920 liters of oxygen, which sounds like a lot, but after all, we are burning a whole kilogram of THF. Okay, I hope that review helped. Rewatch any parts that you need to. If you need a magic number, it is 3. And good luck on the retake.